I'm going to be talking about the directed evolution of proteins. So, most of us are probably familiar with natural selection. First, introduce variation. Second, apply selection. And third, proliferation. As you can see, the gray mice have proliferated, while the white mice weren't so lucky. Natural selection has been the guiding force behind evolution for millions of years. It's very simple and it's very elegant. But because evolution happens so slowly, it's been difficult for scientists to utilize it in a meaningful way. Until now. We're now beginning to hijack the mechanism of evolution to design proteins. An example of this is creating an insulin protein that can survive being digested. Here's how it works. So, step 1, introducing variation. We take our target DNA sequence and run a polymerase chain reaction to create multiple copies. But the trick is that we use a polymerase enzyme that makes more mistakes than usual. We then end up with thousands of copies of DNA, each with small individual errors. So this is our variation. We then take those DNA sequences and run them through in vitro transcription and translation to create thousands of mutated proteins. But there's one more trick. We use a special ribosome that doesn't let go of the protein or the RNA after translating it. This will be important later. So, step 2, applying selection. In the case of creating an ingestible insulin, we test to see if the protein can survive being in a solution of proteases. Proteases are the enzymes in your stomach that digest proteins. We also check to see if the mutated insulins can still attach to the insulin receptor. If a protein is able to survive both of these tests, that means we've created a mutated insulin protein that can survive being digested while still functioning as insulin. Now, because we use that special ribosome, the protein that survived both tests is still attached to its RNA. So we can take that RNA and through reverse transcription go back to the mutated DNA sequence. We can then run that DNA sequence through another PCR. This is step 3, proliferation. By running this cycle over and over again, we can create the perfect protein that is most ideally suited to fit its new function. It's basically just survival of the fittest. The applications for the directed evolution of proteins is nearly limitless. We've already talked about creating insulin proteins that can survive being ingested, so they don't have to be injected. But it doesn't end there. After all, most of our bodies are made of proteins. Now that we've cracked the code of natural selection, we can start taking evolution into our own hands.